My name's Matt. I work on Android. And this talk is going to be about Android, Linux, and Rust. So disclaimer, recent photo of me. I'm brand new to this project. I'm like days into kernel development and a little bit less brand new to Rust development. So you're welcome to talk to me about it in the hallway, but I may refer you back to this slide when you do. But anyway, so what's a good conference talk without a quote from some famous dead guy? So they say, you know, I have seen it further. It is by standing on the shoulders of giants. That's like something we say in software in some way, shape, or form all the time, so much so that it has become cliche. But perhaps it is true no more than with the Linux kernel. All of us, I think you'd agree, in some way, shape, or form are standing on the shoulders of the kernel. Or in Android's case, quoting straight from the kernel documentation, the Android documentation, Android is based on the Linux kernel. And essentially, most of the main security features are just kernel security features that Android is taking advantage of. I'm going to forget some of this, but I only have a couple minutes anyway, so it's all good. So the main thing that Android uses in the Linux kernel is something called application sandboxing. So it just leverages the kernel features that were originally built to separate users from one another to separate apps from one another. So every app that runs on your Android device is running in its own UID, in its own process, and that provides pretty simple security benefits, right? App and process isolation. It's, in layman's terms, how your social media app du jour does not access your banking app's data. But all of these apps running in their own process means there's a pretty heavy inter-process communication load on Android devices at all times. So Android needed to do something not only to make IPC fast, but also to make it a little bit more user-friendly when it first came out. They did that with a thing called Binder. So Binder is a Linux kernel driver along with a corresponding user space API that essentially makes IPC as fast as possible on mobile devices, and also a little bit more user-friendly both for developers and for the Android framework itself. And if you wonder, why Binder? Like, why not just use the existing Linux IPC mechanisms that were in place for years and probably could have suited their needs? And for that, to answer that question, since I'm new to this, I'm just going to stand on the shoulders of giants again. So Diane Hackborn is one of the founding Android framework engineers. You don't need to read this quote, but suffice to say, if Diane said that Android needed a custom IPC mechanism, then Android probably needed a custom IPC mechanism. So 2 minutes in, like, what is this actual project? So why are we rewriting this kernel driver that's been around since the very beginning of Android and Rust? And the main reason is because we can. So thanks to the Rust for Linux organization, before, if you wanted to write a kernel driver, you had to write it in C. As of late last year, you are also now able to write it in Rust. So the Binder driver itself, it's about 6,000 lines of code. It's pretty small, but it has a history of high vulnerability density. Since it's a critical part of Android's sandboxing strategy, it is also a popular target, if not the most popular target, for in-the-wild exploitation. We've had some talks about browsers before. Chrome on Android also wants to run multiple processes, which have to be sandboxed and things like that. So if you get kind of break out of the sandbox with Chrome's renderer process, which was referred to in an earlier talk, you can do very bad things. So most of this is stolen from a colleague of mine, Alice Rule, who's working on this project at Google and is also, if you're familiar with Rust, is the main maintainer of the open source library called Tokyo. So I'm going to take some examples from her that I think are pretty simple. So there are no buffer overflow vulnerabilities in safe Rust. Now, the word safe is kind of an asterisk that I don't have time to address. But the point here is that this screenshot that you see is just a fix for a vulnerability in the kernel driver, and it's super simple. But the point is that the vulnerability itself is not. In Rust, you basically can't do this. So for those of you that are Java, JavaScript, Python developers like myself, if you did something like this and accessed an array out of bounds, you'd get the famous array index out of bounds exception, and your process would crash and everything would be fine. But when you do this in C, you can access memory outside of that array's bounds and perhaps write to other program memory, and attackers can then leverage that bug to do bad things. So Rust would have prevented this vulnerability entirely. This one's not actually really a security thing, but in Rust you can't forget to clean up. So those of us like me that are used to garbage collected languages, you really don't worry about this, but if you're writing in C, you need to ask for your memory, and then when you're done with your memory, you need to give your memory back. But Rust uses this concept at the compiler level called resource acquisition is initialization, meaning once that variable goes out of scope, the borrow checker can just go ahead and clean it up. So for all that mess on the left side, and trust me, there's more, in Rust you have a closing curly brace. So for a newbie like me, trust me, I trust myself much more to write the close curly brace than I do to write whatever is happening on the left. Like I don't want to worry about any of that. And then the last one, and this one's kind of the hardest to explain, and I probably have no business explaining it, but Rust's kind of ownership model prevents use after free vulnerabilities. So in the kernel driver, there's this kind of complex many-to-many relationship between two entities called a process and a node. And you essentially should not access a process once it's dead. So if a process dies, the link between the process and the node should go away. There's a kind of nuanced bug, or there was, that was fixed in this CVE, where you could essentially, it was a dangling pointer and thus a use after free vulnerability. In Rust, you have to rearrange things, but you basically can't do this. So the worst case scenario with this model in the Rust rewrite is a memory leak, which is still bad, but it's more of a performance problem than a security problem. And trust me when I say, when we're talking about this low-level stuff in Android, you'd much rather have a performance problem than a security problem. So that's about it. I guess the last thing I'll say is that the binder driver has been around basically for the history of Android. So it's an old and very successful kernel driver that we are attempting to rewrite, and there is no guarantee of success. So wish us luck. Thanks.